Hi, ladies and gentlemen. Good morning, good afternoon, or good evening, depending on where you are joining this virtual conference from. And hope you are all safe and doing well there under the pandemics. This is Lei Chen Shen, in charge of the R&D division of Miniaturization Competence Center in USI Taiwan. My hot topic today is implementation of 5G mmWave from module to system integration. USI was established in 1976, provides design, manufacturing, miniaturization, industrial software and hardware solutions, and also material procurement, logistics, and maintenance services. Global revenue achieved $7 billion in 2020. Now, we are a member of ASC Technology Holding. USI delivers a wide range of product portfolios from module, subsystem, to complete system, covers wireless communication, computer and storage, consumer, industrial, medical, and automotive electronics. In this presentation, the integration of a module development to an industrial-grade ruggedized handheld devices will be demonstrated to show how a module solution can assist to launch highly competitive products with better time to market. The agenda in this presentation includes a briefing of the challenge in 5G mmWave handheld design, the architecture proposal, followed by the story from module design to the system integration, and finally, a short summary. Enhance the mobile broadband, ultra-reliable and low-latency communications, massive machine-type communications are three key features enabled by 5G technologies. Comparing to previous wireless technologies, one of the most critical evolutions in 5G is the frequency bands, extended to sub-6 GHz up to mmWave. From 4G to 5G, higher speed and better performance are brought to humans' life, especially in latency-critical missions. And high-speed broadband, while it also gives us challenges. It means more bands, more antennas, and much higher frequency what we ever familiar with. Firstly, let's zoom in the evolution of band configuration from 2G, 3G, 4G to 5G. You can see the frequency range was becoming wider and wider. In mobile phone design, to operate with these increasing frequency bands, the number of antennas also increased. You can find one antenna in 2G, 3 antennas in 3G, 4 antennas in 4G. While when 5G comes, there is a big jump of number of antennas. There are totally 13 antennas to fulfill all 5G performance requirements. The challenge is, given a similar space, 13 antennas has to be coexistent with good performance and also good isolation from each other. Next is the architecture design corresponding to the challenges. In the proposed architecture, sub-6 and mmWave were partitioned as two function blocks. In mmWave, a well-proven QTM525 was leveraged, which is the second generation mmWave module, including RFIC, PMIC, and the phase array antenna supporting 5G NR. A system on module based on Qualcomm SM7225 platform was then developed with integrating SDR735, which is a wireless WAN transceiver IC supporting 5G NR sub-6 together with legacy 2G to 4G LTE. Here shows how the 13 antennas were located. Due to time limit, I will not go through every details. You can see the miniaturization, the combination, and the placement of these antennas are three key factors to give good performance with good isolation. Regarding the floor plan, the designed module SOM7225 was mounted in the middle of the carrier board, with the CPU SM7225 exposed to the other side to have further thermal solution on it. To minimize the interference between frequency bands, a cost-effective solution of shading cans are adopted here. There are 7 shading partitions on the SOM7225 and the other 8 populated on carrier board to make sure we can minimize the interference between all frequency. Here comes to the module design. This module includes the CPU SM7225, 4GB LPDDR4, 64GB flash storage, PMICs, clock, SDR735 and RF front-end which support wireless WAN 3G, 4G, and Sub-6, totally with 1010 LGA IOs. If you look at the simulation result in the right-hand side, the PCB material, component placement, layout, and the stack-up can give the low warpage around 53 microns at a module size of 42mm by 60mm, which is far below 200 microns, and can guarantee low manufacturing risk in LGA mounting to the carrier board. This slide gives a snapshot of the module assembly. Double-sided SMT with LGA I/O, 12 any-layer PCB, totally 984 component count, including 9 CSP at 0.35mm pitch. High-density SMT design rule of 150 micron component-to-component spacing was applied here to minimize the module size as small as possible, so that we can better control the warpage. One important thing to be addressed is the PDN, the power distribution network. We know that to minimize the impedance over the frequency range, it requires shortest path, sufficient trace width and vias, and also the proper PMIC and the decoupling capacitor configuration. We also know that higher layer count PCB thickness will increase the impedance and effective inductance. So in the SOM7225, we need to reduce the thickness from 1mm to 0.912mm to pass the PDN simulation. Next, let's move to the system integration and the verification. The sub-6 portion has been integrated into the module SOM7225, while we need an interconnection between SMR526 and QTM525 for mmWave function, in which the IF trace total loss must less than 7 dB at 10 GHz. According to the simulation results, a flexible cable made from LCP can achieve the requirement. The total loss is 5.5 dB at 10 GHz. In handheld devices, usually very high-density design within a tiny space, thermal would be a killing factor. There are 2 aspects to be considered here. First, reduce junction temperature, because you don't want to burn out your CPU. And second, balance the skin temperature on display and the back cover, because you are not allowed to burn your end users. Here, we apply double-sided thermal solutions to the CPU to balance these 2 constraints. Here, we did the thermal tests in sub-6 and mmWave respectively. In sub-6 operation, results showed that the SDR735 has the highest temperature. It's run at 72.75 degrees Celsius, and all other IC temperatures are within spec in 25 and 50 degrees Celsius chamber test. In mmWave operation, results also show that all components in the mmWave modules met temperature spec at 3 different occasions. Let's turn to face the challenges of antennas. Allow me to recap it. There are 10 antennas for sub-6 GHz and 3 for mmWave, totally 13 antennas. There are 2 design concepts in sub-6 GHz antennas. First, if we can have good separation between end of radiators from 2 surrounding antennas, then surely we can obtain optimized antenna performance. Well, if ideal separation is not available, to adapt different types of antennas such as PFAR, loop, coupling, etc. to increase isolation and enhance the efficiency. In our final version, we adopted a variety of different antenna types to achieve the design for the 10 sub-6 antennas without increasing the size of the DUT. mmWave is defined as frequency ranging from 30 GHz to 300 GHz. Currently, 24 GHz to 40 GHz are used for 5G. The key advantage are wider bandwidth and extreme speed. But higher the frequency, larger the transmission loss. Therefore, high-gain antennas are expected. While high-gain antenna usually means that the coverage is not good enough. Thus, beamforming technology was developed to increase the coverage. In mmWave, since we leveraged the proven module QTM525, the major effort here is to accommodate mechanical design and these 3 mmWave modules. Our study showed that a mechanical design with hard contact between QTM525 and the DUT cover did affect the final performance of QTM525. By revising the DUT cover with an arc structure, the mmWave performance was retained. It was a 1.3 dBi improvement of antenna directivity on both 28 GHz and 38 GHz. This is the 3D radiation pattern by the final DUT in mmWave with beamforming activated. Results show that most of the direction has been covered, and the coverage angle is very close to that of sub-6 antennas. After all the development jobs finished, it came to the system verification. 2 devices were taken as benchmark. One is Google Pixel 5, and the other one is the reference design from the chipset provider. Field test data showed a promising result in throughput performance. Since there was no mmWave service available nearby, we took lab tests to benchmark the performance between devices. Results also showed that the DUT could achieve the throughput performance of 3.03 and 3.25 gigabit per second at the mean and the theory throughput respectively. In this presentation, the implementation from module design to handheld device integration was demonstrated. A short summary will be provided as follows. 5G new radio brings higher speed and better performance, which also challenges system design complexity, which include demanding computing power and functionalities to enable rich applications. More and more antennas and bands are required in handheld terminal. especially given a tiny space. Driving antenna combination and miniaturization. There are many success factors in code design optimization, from module to system integration. Proper code chip placement, stack up, and the layout will determine how good your electrical performance can achieve, especially in signal integrity power distribution network. Antenna efficiency and isolation are highly correlated to your mechanical design. As illustrated in this presentation, in sub-6 antenna, the influence between each other need to be well considered. In mmWave antenna, the flexible cable and the arc design on duty cover are critical. An adequate thermal management solution should be capable of reducing the junction temperature and also balancing the skin temperature on display and the back cover. The shading scheme and the material will directly impact the system level interference and insertion loss. By considering all the factors, the presented DUT, an industrial-grade ruggedized handheld device, as also shown in the right-hand side, can achieve promising performance benchmarked with a commercial device, Google Pixel 5, and Qualcomm reference design vehicle. With the advent of the 5G era, leading mobile phone brands are racing to launch 5G smartphone and bringing the future of the Internet of Things into the present. A system of module solution should be an innovation enabler by assisting device makers or service platform providers to launch highly integrated products for the market's needs and services by saving the hardware development time and shorten the time to market. That's all my presentation. Thanks for your attention.